So 2015, everybody get there? We'll get there.
Yes.
Okay. All right. So we have ourselves an interesting picture here that we've never seen before. Man, I should have saved this for tomorrow. This one would have been a humdinger for y'all. Don't look at me like that, Drew. Come on now. All right. So it's telling us that we have an anode and a cathode. We have a metal. We have oxygen gas, an electrolyte paste, and we see electrons flowing in a particular direction. So all things that we should be aware of here, okay? So number one, actually the only question for this one, it says, metal air cells are a relatively new type of portable energy source consisting of a metal anode and alkaline electrolyte paste that contains water and a porous cathode membrane that lets in oxygen from the air. A schematic of the cell is shown above. Reduction potentials for the cathode and 3 possible anodes are given in the table below. So we're given some information. And what's interesting is some of those reactions do not appear on our standard reduction potential sheet. So again, if they're giving you something, might be useful. We don't know. Okay. All right. So A says early forms of the metal air cells used zinc as an anode. Zinc oxide is produced as the cell operates according to the overall equation below. So we have solid zinc with oxygen gas makes zinc oxide. So we go solid gas to a solid. Okay. All right. I says using the data in the table above, calculate the cell potential for the zinc air cell. All right, so here's what's given. So we know we have solid zinc. We know we have oxygen gas. That's what's given, okay? And we know that we're going to produce some zinc oxide. So what should we do? Oh, before I go any further, let's do a little sidebar here, okay? If we have 2 chambers, okay, and you've got your electrodes, and then we've got our salt bridge, okay? That's a beautiful drawing. My gosh, I am such an artist. Look at that, okay? What type of reaction is this? Is this spontaneous or not spontaneous? Spontaneous. So it's spontaneous. And it has how many chambers? 2. So 2 chambers. Over here, if I had one chamber with, say, 2 test tubes in there, and I had my, dang it, water in there, and then I had my, and then another one, and then a battery over here, what kind of reaction is that? Non-spontaneous, okay? So one thing I want you to recognize is, actually a couple things to recognize. We have 2 chambers here on the left, and we have 1 chamber here on the right, okay? Bless you. Do we have a salt bridge with this beautiful drawing on the right? No. Do we... is there an oxidation reduction reaction taking place in the chamber on the right? Oxidation reduction. Is there oxidation reduction taking place in the or the design on the right? Yeah. Is there oxidation reduction taking place on the left? Yeah. So both of those are still having oxidation reduction. What type of sign do we want delta G for this shape here, or this structure? Negative. And we want our voltage to be as positive as can be. Okay. Over here, we want delta G to be positive, and the voltage negative, but not so negative. Okay. Okay. So it's negative, but we're going to say small negative. Okay. Yes, that's what I wanted to talk about. Okay. So with that information that we just provided there, Is this a one chamber or two chamber situation? Dan's holding up 2 fingers. Kern's got 2. Oh, Stark held up 1. Oh, Abby's flashing. Why is it a 2 chamber? There's no outside electrical source. Okay. In other words, we're doing something. We're doing something on this side of the quote unquote battery, and the electrons are moving in that direction. Okay. So typically with an electrolytic system or an electrolysis system, you don't see the flow of electrons. You have to determine that. And sometimes they don't even ask that. But here, we're going from here, and we're moving electrons in that direction, and we don't have an outside source. And as a heads up, the 2-chamber system, I think I have a picture of one here. This is also known as a battery. That's an early battery. This is a, where'd you go? This is the newer form battery, so to speak. Okay. So batteries produce a negative delta G with a positive voltage. So we're generating. Okay. So to answer the question, let's go, which 2 half reactions should I use to answer part I? Should I use the first one? Should we use the first one? Give you another hint. What do I start with? Zinc and oxygen. Should we use the first one? Yes, we should. Okay. That was an easy decision. What about the second one? Should we use the second one? Yes. Why? Has zinc. And the other ones don't, I don't see zinc in any of the others. Okay. So the nice thing is these are reduction potentials. And so we need to flip which one? The second one. Okay. So when we write this out, actually, I'll find a space to do that. So we've got our, I'm going to go small here. Okay. So I've got oxygen plus 2 waters plus 4 electrons generates 4 OH, and it has a voltage of positive 0.34. Okay. Did I get the right one? Yeah. Okay. And then we're going to flip the zinc. I'll use a different color for that one. So zinc plus 2 OH. Zinc plus 2 OH. That's all there is. Makes zinc oxide plus water plus 2 electrons. Okay. And it has a voltage of positive 1.31. Okay. All right. So then, did we answer part I yet? Nope. We're not done yet. Okay. Or did we? Using the cell potential, calculate the cell potential. Okay. So now we do what? Add those up. So 1.65 volts. Now, let's make sure that this all works out fine and dandy. So if I want to balance electrons, I have 4 electrons up here, so I need to multiply the bottom by 2, so my electrons go away. How many OHs do I now have? 4, they go away. And then how many waters do I have here? 2, they go away. So what remains? Oxygen, zinc, and zinc oxide, but 2 of those, so 2 zinc. So if you're not 100% sure, double check and say, hey, does that even balance out to get us to where we were at? So yeah, we like that. All right. Everybody good with I? Easy peasy. Double I. The electrolyte paste contains hydroxide ions. On the diagram of the cell above, draw an arrow to indicate the direction of the migration of the hydroxide ions through the electrolyte as the cell operates. Okay, so we have hydroxide in here. Let's go a little thicker. Dang it. Okay, so we'll go chunky here. So we have hydroxide in the electrolyte paste. The question wants to know, are we going to go this way or this way? Which way are we going? To the left or to the right? To the left? Why? Very good. So we know there's a couple reasons. As you look at the metal, which is, oops, don't erase it. It's zinc, and it goes to zinc +2 to form the zinc oxide. So that means that the zinc is changing. Also, which direction are the electrons flowing? Clockwise. So that the charge on electrons negative. So we want to keep the flow, the negative flow, moving in this direction. So it is a clockwise flow. So the electrons move up the wire to the right and down, and then the hydroxide must flow toward the left. Now, does it say justify? No. It does not. But if it were to ask that, you could answer that in one of two ways. You could say the flow is clockwise. Sorry, clockwise is this way for you guys. Okay. Yeah, that way. Okay, so clockwise, the flow is that way. Or, like what Abby said, is that you're becoming more positive, so the negative charge has to flow in that direction. Good. Not so bad yet. B, a fresh zinc air cell is weighed on an analytical balance before being placed in a hearing aid for use. I don't have those yet. I'm there. I'm getting close. As the cell operates, does the mass of the cell, this is the cell, does the mass of the cell increase, decrease, or remain the same? Increase, decrease, or remain the same? And let me erase all this. Think about that for a second. So is the battery getting heavier, lighter, staying the same? What's that?
That oxygen. Is that oxygen like part of the cell, or is that just like the atoms?
That's a good question. What would you guess a metal air cell deals with?
Metal and air.
So the metal with air. Okay, so all the air that's around you. So when we look at this, I'm glad that they didn't do this and put like an arrow, because that kind of gives it away. But really, that's what's happening. So we don't have oxygen in this initially. But when oxygen comes into play with this, what are we forming over here? Zinc oxide. So we start with just zinc, and then later, as the reaction proceeds, we make zinc oxide. How do we know that? Because the equation tells us so. So right there, that's given us that information. So the mass of the cell should increase. And then, crap, it didn't even ask for an explanation. Oh, here it is, double I. Justify your answer. So you're bringing in outside oxygen, which has a mass. I know we all think of gases being light in weight, but it does have mass, 32 grams per mole. And then justify, it says justify your answer in BI in terms of the equation of the overall cell reaction. So in other words, based on what we did up here, we introduced the oxygen. It reacted with the zinc to form the zinc oxide. Zinc oxide is heavier than zinc itself.
If it was a gas that was like in the cell, then the mass would have changed.
Correct, but this would be a very short-lived cell. Yeah.
Because the gas would be used up.
Immediately. Yeah, and remember that a gas is mostly made up of what? Empty space. So, oof. So it's much more efficient to bring that oxygen that's available or grab it from what's around.
If there are hearing aids in space. Right, if you wear a hearing aid,
You're going to be deaf.
you wear a hearing aid and you're like in a space station with limited oxygen, you know.
Well, if you're breathing, then hopefully there's enough for your battery.
Well, true.
Good Lord.
I don't know. I don't know
Ah.
what the consumption looks like for that. Like, is it like another person's up there with you, or is it like?
Man, that's going to get hot in that ear. All right, part C. Good question, Dan. I just don't have an answer.
Okay.
All right, the zinc air cell is taken to the top of a mountain. To the top, where the air pressure is lower. Ooh. Okay. So will the cell potential, aka voltage, be higher, lower, or the same as the cell potential of the lower elevation? Before you answer that, fun fact. We always like fun facts. That if we are here at sea level, here, let's make that not so chunky. I'm chunky. It's okay. So mountain. Okay. So sea level. So the percent of oxygen is around 20% at sea level. What do you think the percent of oxygen is at the top of the mountain? 20%. Very good. The percent is the same. However, the amount of air particles is a lot less. Okay. So we don't have as many air particles. So maybe we have 5 air particles up there. Up here, we're not going to have 5 air particles. Maybe 2. I know. Okay. So air particles. Okay. So this is a Q problem. Not a U problem, it's a Q problem. So what is the equation for Q here? Okay. What is Q equal to? So it's products. I'm hearing products over reactants. So what would my product be that we care about? Well, okay. What happened with the zinc here? Is it oxidized, reduced? It's oxidized, so we do have zinc plus 2, but we don't care about that. Okay. And then what is my reactant that I care about? Let's see if you remember. Can we place gases in a Q?
No.
Yes.
What?
Gases and aqueous. No solids or pure liquids. Gases all day long. Remember, gases are mostly made up of empty space, so we can change its molarity. So we can put O2 down here. Okay? So let's assume that zinc is 1. I don't care what it is, but let's just assume it doesn't change. So as we get higher on the mountain, is my voltage going to go up, down, or remain the same? But before you answer that, what's happening to Q? Is oxygen's value going up or down? Down. So let's say that it was originally 1, now it's 0.5. I'm just making up a number because it's easy for me to do that. So now Q is equal to 2 versus 1. So if I take the log of Q, is that a positive number or a negative number? Positive. So when you plug it into Nernst, which we love so much, you got to love Nernst. So, not up there. Sorry, my bad. 0.0592. So log of Q. So this becomes more positive, which makes this more negative. So the voltage goes down. So it decreases as you climb the mountain. because we have less oxygen available because of our Q equation. So when you see a question like that, think of Q. Okay. I just gave the answer to. Shoot. So double I. And the information above. Oh, D. Here we go. No, you good. You good. Shot. Oh.
Grab these crumbs.
All right. Part D, as in dog. Donuts.
Oh, you can like the bottom of the bag.
I'm good. All right. Part D says metal air cells need to be lightweight for many applications. In order to transfer more electrons with a smaller mass, sodium and calcium are investigated as potential anodes. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of the cell? And then justify your answer with a calculation or with calculations. So what should we do here? Never. When you see grams, convert to moles. Okay. So we have 1 gram of sodium and 1 gram of calcium, was it? Okay. So we're going to find out in 1 mole of sodium, it's 22.99 grams. And then 1 gram of calcium, 1 mole of calcium, that's 40.08 grams. Okay. So what do we want to do next on this? Determine what?
How many electrons you get per mole?
That's facts. So no Faraday.
What?
So in 1 mole of sodium, how many electrons do you produce? 1 mole of electrons. Well done. Because we know sodium wants to be +1. And in 1 mole of calcium, 2 moles of electrons. Now, you can do the calculation, but who has... if I divide this in 2, I get 20.04. So who really is well, let's just find the math. I don't want to mess you guys up. Sorry. Yeah. So it's wanting to know how many. So 1 divided by 22.99. Is she all right?
I don't think so.
That's all right. That's pretty normal. 0435. Okay. And then this one is 2 divided by 40.08. So 0.04. No, we'll say 50. So which one produces more electrons? Calcium. That's your justification right there with calculations. We're making more electrons with a smaller mass or same amount of mass. Okay. So the higher the number of electrons, that's the one we want. So more problems. We like problem solving. That's good. Math. Yeah. Oh, wait, shoot. Where did we go? Here we go. All right. E. The only common oxide of zinc has the formula ZNO. Thank goodness. Write an electron configuration for a zinc atom in its ground state. Normally it's, you don't have to use, here, I'm gonna let you decide. Don't use, I want to do it without giving it away. Don't use shorthand. Because I said so. because it didn't say. It didn't say you could. Don't. Nope. Don't. And done. You're done too? What are you waiting on? Come on. That didn't even freeze it, did it?
No.
Well, I don't like this thing. Okay. So there is your electron configuration and its ground state. What does ground state mean again? Not neutral. Means all the electrons are as close to the nucleus as possible. Okay, so nobody's excited. Nobody's moved to a higher level. All right. Double I. From which sublevel are electrons removed when a zinc atom in its ground state is oxidized? What the heck does oxidize mean? Losing electrons. How many is it going to lose? 2. And it does normally have a +2 charge. So are we going to lose 2 electrons from the 3d10?
No.
Why? The weird rule.
And plus, if 4s will give it up. It's not selfish.
You guys are the smart class. Everybody else was like, oh, yeah. We always take electrons from the higher energy level first. And the dumb rule about we want to make sure that D is, if we can have a full D or a half-filled D, we're going to do that. So if you take an electron out of the 3D, the electron that was in the 4s is going to move over. So we're actually taking it from the 4s. Again? All right. So let me stop this one. Oh, I don't know what that did.
Wow.
Hang on here.
Wow.
Hang on.
That's a keypad.
That's my